start by saying how honored I am to have been invited to participate in this program. I've been very impressed with the group of young women scientists here, and I can't wait to see you take over the laboratories in universities. So please do so quickly. Thank you. Okay, so I know most of you probably do not study astrophysics. Well, let me ask, how many of you have studied astrophysics? Oh, maybe closer. Closer? Astrophysics? A few. Okay, one actually. Okay. So I will explain everything as we go. Let me start by talking about what a galaxy is. It's a gravitationally bound collection of stars. This is a typical spiral galaxy named after its, obviously after its shape. We believe that the Milky Way galaxy that we live in looks like this one. But of course, we cannot take a picture of our own galaxy because we're inside it. So we use other galaxies as a proxy, and if this were our galaxy, then we would be out in the suburbs. Our sun is a star in a very unexciting part of the galaxy, in a spiral arm pretty far from the center. This is good news for life. We were just talking about life. It's good news for life because the center of the galaxy has too much ultraviolet and X-ray and gamma ray photons, which could penetrate the atmosphere, particularly before oxygen, and mutate all life and make it difficult to survive. High energy radiation is as good a sterilizer as oxygen. Okay, it also turns out that every galaxy, including our own, has a supermassive black hole at its center. By supermassive, I mean 1 million to 1 billion times the mass of our sun. And those black holes were probably not born or created being that massive. Smaller black holes were created. We'll discuss how in a few minutes. And then over time, they grow by adding matter. Matter falling into the black hole increases its mass. Okay, so let me start by, oh, right. Also, there are many kinds of galaxies, not just spirals, as in the lower left, but barred spirals, round galaxies, strange galaxies. So I will also discuss a little bit about how the different galaxy types arise. So first we have to start, when we talk about black holes, we have to talk about gravity. Gravity, how many of you took physics class already? Should be almost everyone. Really? Not everyone? Okay. Please, we must have more physics training. Okay, well, Sir Isaac Newton, as we heard 2 days ago, very famous physicist, he basically created calculus to explain and created a law of gravity, a thought of gravity, that fully explained the motions of the planets. I think Leibniz would dispute whether he created calculus, but in any case, he put modern physics on, he created modern physics. And much of what we understand about black holes can actually be understood from Newton's description of physics. The idea of dark stars was mentioned about 100 years after Newton wrote Principia by two different scientists, John Michell and Pierre Laplace. I'm going to tell you about John Mitchell's idea about dark stars. He said, if there should exist in nature any bodies whose density is not less than that of the sun and whose diameters are more than 500 times the diameter of the sun, then their light could not arrive at us. He's actually talking about something called escape velocity, which I'll describe in 1 minute. But an interesting, the second thing he says is, if we would not be able to see those bodies, yet if any other luminous bodies should happen to revolve around them, we might still, perhaps from the motions of the revolving bodies, deduce the existence of the central ones. So he actually understood much of how we measure black hole masses today. And in this movie, which I think I have to start, this is a movie of stars at the center of our galaxy, done by Andrea Gheza's group at UCLA. Can you see it okay? Yeah. What you're watching are the trajectories of stars in the vicinity of the center of the galaxy. And I want you to notice a couple of things. First of all, the stars closest to the center move much faster than the stars farther out. And also, they seem to be circling some invisible mass. This is extremely easily explained by Newton's laws of gravity. So for the students in the room, you learned Newton's law of motion. Gravitational force equals mass times acceleration. And if you think about a star orbiting a mass, and for simplicity, let's just assume it's a circular orbit, then you can relate the gravitational force. This is Newton's law, that gravity, the strength of gravity is proportional to each of the masses, the product of the masses, divided by the distance between them squared, and with Newton's constant g. And you can set that equal to the mass times the centripetal acceleration, which is given by the speed of the orbit squared divided by the radius of the orbit. This equation, you notice the mass of the black hole is the big M. The mass of the thing that's orbiting cancels out, okay? Doesn't matter, it's a test particle. So you can solve for the mass of the black hole in terms of the speed of the orbit, the radius of the orbit, and Newton's constant. So going back to the stars at the center of our galaxy, this is another movie by Andrea, but focusing now only at the central stars. For each of these stars, you can calculate the mass of the unseen object that they are orbiting. And what she and Reinhard Genzel have shown in a competing team in Germany, that the mass of that object is 3 to 4 million times the mass of our sun. And that is the best measured black hole mass in the universe. And I predict Andrea should get the Nobel Prize for this discovery. I knew Andrea when I was a postdoc. She was an undergraduate at MIT. So I look at this room full of students and I think, which ones of you will get the Nobel Prize for your work? Yes, I hope to see it. I expect to see it. Okay, let me talk about escape velocity. If I threw this bottle of water up into the air, it would fall down, okay? If I threw it really hard, I could get it to hit the ceiling. If I went outside and threw it really hard, it would go higher. And if I asked NASA to throw it really hard, it could be launched into space, okay? If I could give it sufficient speed that it could escape the gravitational field of the Earth, that initial speed is the escape velocity, okay? And of course, more massive objects have higher escape velocities than small objects. A black hole has an escape velocity that is greater than the speed of light. Since no particle can move faster than the speed of light, nothing escapes a black hole. So one way to think of a black hole is a body who has a very high escape velocity. This cartoon just shows this. If you had a very tall cannon on the top of a mountain somewhere and shot the cannonball, as you increase the energy with which you propel the cannonball, it goes farther and farther. Eventually it could orbit the Earth, or it could escape altogether. So that, again, just escape velocity. Okay. But black holes really have to do with Einstein's theory of general relativity. They're inherently a general relativistic thing. There's Albert. How many of you have studied general relativity? Okay, more than I expected. But for those who haven't, we will study it today in 2 slides. So Einstein was unhappy with Newton's law of gravity because Newton's law of gravity said this body over here and that body over there have a gravitational attraction that is instantaneous. Now, you weren't here an hour ago, so you came into the room and you came into the room. When did the gravity exist, and how did your body react to the gravity of that body? In Newton's law, it's instantaneous, okay? And Einstein knew from having developed his simpler, earlier theory of special relativity that light and any signal takes a finite time to propagate. So for example, when someone walks in the door, it takes a certain amount of time for me to see that light. Of course, light travels very quickly, and I see them almost instantly, but there's still this delay. And in Newton's law, there's no delay. So Einstein did not care for that formulation. So he created a different theory of gravity in which is not described as the force between 2 bodies, but instead every object with mass deforms space around it. And he talked about the curvature of space as the quality of gravity, if you like. So all of his theory, oh, sorry, right, I have to introduce singularities. Yeah, sorry. Okay, how many of you have heard a black hole described as a singularity? Have you ever heard that? Not so many. No, maybe, okay. Some, and then some shy people, okay. Okay, I'm about to explain it, thank you. Thank you, Joan. Excellent. So I should say, this slide is one that I give at talks where people have no mathematics. So I apologize that it's overly simple. But some people, yeah, okay, I just said it. This is a fraction with x in the denominator. If x is 0, this is a singularity, represents a singularity. If you like, the fraction has no value. It's not defined at x equals 0. So at x equals 0, this fraction has a value of infinity. Now consider a fraction that has a different denominator, x minus r, where r is just some, let's say, radius of a black hole, okay? Then as x goes to r, that is a singularity, okay? Now, why is that relevant to Einstein? Einstein's theory replaced the idea of force of gravity with the idea that matter causes curvature of space. And then he described the force of gravity effectively by something called a metric, which just means the distance between 2 points in space-time. Not just space, but space-time. Space-time is the 3 dimensions of space, x, y, and z, plus the dimension of time. Okay. So you are familiar with a metric. The first one you learned was the Pythagorean theorem, which tells you that for a right triangle, the distance of the hypotenuse, oh, I guess I didn't write it down. Yeah. The distance squared is equal to the sum of the squares of the 2 legs. In my popular talk for the public, this is where I show a clip from Wizard of Oz. But since you're science students, you don't get to see the movie. But it has a weird reference to the Pythagorean theorem, which I invite you to look for next time and remember. Okay, in general relativity, the Schwarzschild metric is the answer, if you like, for the very simplest case that anyone can imagine. So it's a universe which is completely empty of any matter. No people, no EY University, no Earth, no stars. There's one piece of matter, of mass m, at a point that's the origin in the coordinate system, okay? And in that universe, which has only one thing in it of mass m, at a point, that is called a Schwarzschild universe, and the metric for that case is this kind of messy equation, where the distance squared in the metric is a space-like part and a time-like part. And I want you to focus on the space-like part and notice that it has a denominator which can go to 0. So let's look at that. There's the denominator in that expression. And you see there's two places where you have a problem, okay? One is when, well, you have singularities, effective singularities at r equals 0 because of the right-hand term, and at r equals this 2gm over c squared, because then the expression is 0. Now, for the experts, these are not, the second one is not formally a singularity. It's a result of using this particular coordinate system. But in any case, those are two special places in space in this Schwarzschild universe. One is the location of the black hole, and the other is its radius. Okay? Black hole is located at the center of the universe, and the radius of the black hole is this quantity, 2gm over c squared. Because Schwarzschild solved this problem, that's called the Schwarzschild radius of a black hole. It depends only on its mass and two constants of nature, Newton's constant for gravity, and the speed of light, which is the c, little c. Notice that the radius of the black hole is linearly proportional to its mass. So you may have heard that black holes are very, very dense. In fact, if we took, the mass of our sun and stuffed it into a black hole, it would be very small. It would probably be, I have it on the next slide, about the size of the center of Sol. Very, very small. But if you make it as massive as the black hole at the center of our galaxy, or the black holes that I study, which are 100 million or 1 billion solar masses, then the density, the average density, is the density of water. Because, of course, as you increase the mass, the density depends on mass divided by radius cubed, okay? So it's proportional to 1 over the mass squared, right? So as the mass goes up, the density goes down. That's just a little interesting fact you can entertain people with. So inside this horizon, the escape speed is greater than the speed of light, so no light gets out of the black hole, no particles, no photons. Here are some examples of size and mass for black holes. For example, if we could take the Earth and stuff it into a black hole, okay, make it a black hole, then its size would be about the size of a marble, 1 centimeter on a side. A star that's 10 times the mass of our sun has a radius of 3 kilometers. The Milky Way black hole, which is 3 million times the mass of our sun, has a radius that's a tiny fraction of the Earth's orbit around the sun, so very, very small compared to the galaxy. And much larger black holes have radii that are several light hours. I did the calculation just to see how big a person would be if you made them a black hole. And that's smaller, 10 to the minus 23 centimeters, is smaller than any known particle or anything. Now, in nature, we only know about 2 kinds of black holes. The ones that are a few times the mass of our sun, and then the supermassive black holes that I will be talking about. The stellar black holes are the remnants of stellar evolution. So if a star is massive enough, after it has consumed its fuel and made the heavy elements that are in your bodies, you know, right, that every atom in your body has been through a star, has been in the center of a fiery star. Well, the reason those elements are in you or in our Earth's crust or in the food you eat is because at the end of the stellar life it blows up and it spreads those atoms across the across the galaxy. And so when an Earth forms, it forms from heavy elements that then become food and people. But I'll just be talking about the supermassive black holes. Okay, this is like the intro part. Are there any questions so far? You with me? You got the whole thing? Okay. Okay, so now we do the fun part, which for me is the observing part. I'm going to skip the scales of the universe because it's long. So I'll just... The universe is really big. And sort of the size of the universe at the present day is maybe of order 10 billion light years across. And that's the scale on which I'm looking. Many of the galaxies that I observe are billions of light years away. That means the light that we are detecting today was emitted before the Earth even existed. So my research group, this is a project I started just before I moved to Yale. Let me see how to say this. Yeah, I skipped a bit of intro. So I told you earlier that we know there is a black hole at the center of every galaxy. We know that because we basically, whenever we can measure the mass at the center of a galaxy, we see that it probably is a black hole. But before that, there were some special galaxies, which we call active galaxies, which have a source of light in their centers that's extremely strong, much stronger than the stars that we see in most galaxies. And that light comes from the following. Matter falls onto the black hole, and as it falls in, it gains energy. So before it gets to the black hole, it actually creates a lot of heat and light. And that light is very, very strong. It can outshine the stars in the galaxy by a large factor. So those special galaxies, we already thought had to have supermassive black holes in their centers. And we can study them to understand the process of how black holes grow. And most of those studies were based on observations made with optical telescopes on the ground. So they are primarily observing rest frame ultraviolet light from these accretion onto these black holes. But I knew that it's very easy to block UV light from our telescopes. All you need to do is put a little bit of dust in front of it, and all the UV light will be scattered and you won't see it. This is why the sky is blue, because blue light is scattered more efficiently than red light. So blue light is scattered in every direction, so when you look around the sky, it's blue in all directions. Okay, so I had an idea for how to detect accreting supermassive black holes because they emit a lot of X-rays. And I thought if we did a survey using X-rays, we could, which are much harder to block because they're more energetic, then we could get the true number of black holes. My friends who did the optical surveys thought they had the true number, but I suspected they had undercounted because they missed the ones that are shrouded. So my experiment was to try to find and count all the supermassive black holes, their number, their masses, their distances, their ages, and to understand how they interact with the galaxy around them. Now, because I have a finite lifetime, I did not intend to actually count all the supermassive black holes, because there are billions of them. But to do a census, so to do a survey of a representative part of the sky and count those. And the way I did that, well, this is actually some of our data. Okay, yeah. I did it by imaging the sky, a small piece of the sky about the size of the full moon, with some telescopes I'm going to tell you about. But first I want to explain what we look at when we take an image. This is a two-dimensional image representing a three-dimensional space. So some of these galaxies, everything you see in this picture is a galaxy. This one you can probably see is a spiral galaxy. And this one's an elliptical galaxy. The brighter ones are nearer to us. And the really, really faint ones are far away and also redder. So let me see. Yes, here is a little red spot that if you're in the very front, you may be able to see. That's probably the highest redshift galaxy in this image. So let me show this little, I'm not going to show that one. Let me skip that. Let me show this movie. Hello, wake up. There you go. This movie sort of shows you how a photograph like I just showed you is really three-dimensional. So this is the same image, slightly lower quality anyway. And this is a movie of what you would see if you could drive through space at many, 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 many times the speed of light, okay, because these galaxies are far away. We're passing galaxies that are 1 million light years away, and soon we'll be passing galaxies that are 1 billion light years away. So the first thing you see is that the brighter, bigger ones are mostly nearby, although there are also small, faint ones nearby as well. And you might be able to detect that they come in clumps. Galaxies like to live in groups because of gravity. Gravity pulls more dense things together. And now you see that sort of there are fewer and fewer galaxies, and there's more dark and emptiness. That's not real. That's just because our telescopes can't detect things that are far away. So we are reaching our limit of being able to detect things, and the few things we can detect are extremely luminous. So that's an object that's incredibly luminous. Okay? So now you have a sense of what those images are showing. And now we want to ask, out of the 80,000 galaxies in this image, which ones have accreting black holes? You can't really tell from this picture. Yeah, some with bright centers, like this object, might be a quasar, one of these active galaxies, but it's hard to tell. So what we did is use not only, we used 3 different NASA observatories, the Hubble Space Telescope, very importantly the Chandra X-ray Observatory, which detects X-rays. You have to do that above the atmosphere because X-rays do not get through the atmosphere, which is good for us, but bad for X-ray astronomy. I mean, it means we have to fly satellites to do the science. So we use Chandra. We also use the Spitzer Infrared Space Telescope. And that's because if the ultraviolet light from an accreting black hole is absorbed by some kind of gas or dust surrounding it, then it will heat that gas and dust, which will then re-radiate thermally in the infrared. So if we may not be able to see them in the optical, but we should be able to see them with the Spitzer Space Telescope. That was our hypothesis. Okay, and we also use ground-based telescopes. These are the 2 Keck telescopes in the foreground. Keck telescopes are on Mauna Kea on the Big Island of Hawaii. And just to the left of the left Keck telescope, you can see the Subaru Japanese 8-meter telescope. The 2 Keck telescopes are 10 meters in diameter each. 10 meters is like from the front of the room to the back of the room. So that's the diameter of the mirror, and there's 2 of them. Huge. The ones in space are much smaller, sadly, because it's really hard to launch big things. But if you wait a few years, in 2018, NASA will launch the James Webb Space Telescope, which will be 6.5 meters in diameter. And the way they're managing to launch that is the telescope has a center part and then petals that fold. So they'll launch it in the folded configuration. And then they'll unfold, we hope. Okay, so we use these telescopes, and the survey, my survey was called GOODS, because everything in astronomy has an acronym. It stands for Great Observatories Origins Deep Survey. Great Observatories, because that's what NASA calls its Hubble, Spitzer, and Chandra observatories, the NASA Great Observatories. And Deep Survey, because it was the deepest picture of the sky, the longest exposure, if you like, ever done on that size patch of sky. And then we inserted the word origins, partly because we were trying to look at the origins of black holes and galaxies, and partly because if we did not add another letter, we looked very arrogant. I kind of liked the GODS survey, but I was outvoted. Okay, so now what did we find? I'm going to show you two pictures. This one, it's a little bright in here to appreciate the full depth of it, but this is basically a tiny part of the total goods field. We're just focusing on a little part of it. You're looking at the image that was taken with the Hubble Space Telescope, so optical light, and everything you see is a galaxy, as in the big image I showed. The three circles show where in this part of the image there are X-ray sources, strong X-ray sources. So those are our candidates for accreting black holes. And the color of the circle is actually dictated by the X-ray, the characteristics of the X-rays we detect. The white circle is strong X-rays at all energies, and the two yellow circles are strong X-rays at high energies, but at lower energies, the X-rays are missing. And that's the signature of absorption, because low energy or X-rays can be absorbed by gas and dust. So our idea is that these two objects should be the things I'm looking for, the hidden black holes that are shrouded by gas and dust and not visible in the optical. And you can certainly see they're not visible in the optical. The bottom one is undetected in the optical, and the top one is just very faint. Now, if my hypothesis is correct, then when we look in the infrared, all three of those objects should be strong emitters because they'll re-radiate the absorbed energy. And so here is the same image now with the Spitzer emission overlaid in red. And you see that indeed we detect all three X-ray sources strongly. So in fact, those are active galaxies, accreting black holes. Of course, we detect a lot of other galaxies as well. And this is why the infrared is not the place to start looking, because of course the active galaxies radiate in the infrared, but so does every single galaxy, because stars radiate in the infrared. They're thermal objects. So we had to do a very complicated analysis of these data to prove that we had found a population of black holes. And I had a thesis student who did that very nicely, Ezekiel Trester. Okay, so what we found many previously hidden black holes. In fact, we quadrupled the number of black holes, supermassive black holes in the universe. And that is actually highly significant because as you increase the mass that was accreted over time, you have to, it has to be accreted more efficiently, producing less light because we've already counted the light. And so now we realize that light comes from much more accreted mass. So it changes the efficiency of accretion onto black holes that that theorists have to work with. The second thing we found, it was known before actually, is that as you look farther and farther away, remember objects that are farther away, the light has taken much longer to get to us. So we're basically looking back in the history of the universe. So the more distant objects, there are many, many more active galaxies than at present. So that's kind of neat. They were growing back then, and now the universe is pretty quiet. And we're also looking into the issue of feedback, actually quite a bit. I have quite a few students looking at this, but we don't have a simple story yet. Other than to say theorists love feedback. This is the theorist invention because their theories using only gravity fail to predict the universe as we see it today. So they put in something they call feedback, which is just energy from accretion onto a black hole, and by tuning the knobs, the right amount of energy at the right time, they can make their theories match the universe. Unfortunately, when we look for this feedback, we don't see it. So I think the theorists have that wrong, but still working on it. Okay, so now I'm just going to spend a few minutes at the end of the talk to talk about how this fits into the overall evolution of the universe. And this cartoon is meant to show, to represent the universe with time moving from left to right. So we start at the Big Bang, and in fact, inflation is this rapid increase from basically subatomic scale of the universe to macroscopic scale, like the size of the room. And then and then to the right, we don't actually show the expansion of we take out the uniform expansion. So what you're looking at is excess above or below a constant expansion of the universe. And to today. And the drawing just shows you how the universe started out very smooth, and through gravity, it got clumpier and clumpier until stars formed. So the first stars form. They're extremely massive. They live a short time. They blow up and leave behind black holes. And then those, of course, formed at the densest part of the universe, so that's where galaxies are forming. So it's very natural that black holes are at the centers of galaxies, that they would have formed there. And my survey is really sampling this sort of middle-aged part of the universe, about between 2 billion and 10 billion years ago. The universe is exactly 13.66 billion years old, we now know. So our survey went back to like the teenage years. Okay, now I'm going to show a bunch of movies, and this is a very old movie, but I like it because it's simple. Theorists are able to compute the evolution of the universe. Now they can't follow every atom because the computers aren't big enough. And in fact, in this simulation, each particle represents hundreds of galaxies, basically. This is because it's an old simulation. But what you'll see is how gravity over time pulls matter together, okay? And in the upper left is this number Z, that's the redshift. For some reason, this movie starts at a redshift of 28.62. Seems awfully precise, but anyway. At a redshift of about 20 is maybe when the first stars formed. And then at a redshift of 10 or less is the very most distant things we've ever been able to observe. And a redshift of 0 means today, okay? And what the redshift indicates, besides distance, it really is about the scale of the universe. So relative to today. So at a redshift of 9, 1 plus z will be 10. So the linear dimension of the universe is 10 times smaller at redshift 9. So the volume is 1,000 times smaller at redshift 9, okay? All right, let's see how this plays. There we go. So you can see over time, and there's the redshift counting up in the upper left, that all of this matter forms into clumps, which are basically galaxies and clusters of galaxies. And the next slide is the same movie, but now rotating, so you can see the three-dimensional structure that forms. And this is very much like the universe we live in today. Our galaxy is a galaxy along one of those filaments in clusters of galaxies. Okay, now, during that gravity action, there are lots of galaxies that are merging. So in this simulation, a theorist has made two galaxies, which are actually very similar, and they interact only gravitationally. Okay, so what you see are the stars in the galaxies being pulled out of the galaxy through tidal forces. I'm going to run this one again because I want to talk about how that works. Okay. What is happening is the near side of this galaxy pulls harder on the near side of the other galaxy and weaker on the far side. So this tends to stretch both galaxies. That's what tidal usually means. And stars are being flung out into space because of the gravity from the other galaxy. Now these had a low enough relative velocity and high enough mass that they actually end up being one galaxy. And that we think this is how round galaxies are formed, elliptical galaxies. Okay, there are black holes in these galaxies, almost certainly. And so they have to also merge, and I'll show you that at the end. That's the very last movie. But, oh, sorry, I forgot to say, this process that we just saw in 5 seconds or so takes about 200 million years, okay? So that was fast forward. So we never see that. We don't see two galaxies moving by each other. What we see are galaxies that look like this. Two galaxies near each other with long tails, which are tidal disruptions. And these two are passing for the first time, okay, because they're not terribly disrupted. And we can see, well, let me show you. This movie This movie is a similar kind of simulation of two galaxies, but now they stop the film and compare to real galaxies, which we see on the sky. So here's the interaction proceeding. And when they stop it, they have to, in order to match what we see, they may have to rotate the image. Okay, and now look, here's a real pair of galaxies. I think there are about 8 of them. And as so you can see, as the interaction proceeds, you see all of these stages on the sky, all of these stages of mergers. Now, they don't agree perfectly because the merging galaxies aren't precisely these masses and orientations. But you can tell that we've sort of got the right idea. This galaxy is called the antenna, which you guys won't even understand because we don't have antennas. Antennas are what you need to watch TV with if you don't have cable. But you don't have them because you're too young. Okay, anyway. Or maybe that's the antenna. Yeah, that's the antenna galaxy. I think there's one more. These are all images taken with the Hubble Space Telescope, by the way. Okay, that guy disappeared. So we understand that process of mergers, and sort of gravitational collapse is basically the driving formation thing happening in the universe. Okay, from the properties of the host galaxy, if we look at them closely with the Hubble Space Telescope, we can tell from their morphology whether they had a merger recently or not. And we can tell from their color how recently the stars formed, because stars, when they form, they're more blue stars, but they live the shortest time. So over time, the collection of stars gets redder and redder. So it's kind of a clock. And we can also tell whether they're in a very rich, highly clustered region of the universe or not. So we're working on all these issues right now. Okay, my last set of movies, my last movie concerns this particular galaxy. It's called NGC 6240. That stands for New General Catalog. And it's the 66,240th object in that catalog. Very imaginative. Okay. You're actually looking at the center of the galaxy. You notice it doesn't look spiral or round. So based on the last 5 minutes of education, you might guess that this is a merger in process. Okay? And the 2 blue spots that you see, those are 2 black holes that are accreting. One from each galaxy, and you can see that they're approaching each other, and eventually they will merge. Those blue things were detected in X-rays. So what we're showing as blue light is actually X-rays, and the rest was infrared image of the center of that galaxy. Okay, this movie is like one you've just seen. It has a merger, but it's going to get to the black hole merger. So this is actually an old merger. You can see it doesn't have as many particles. Here's a real galaxy, NGC 6240. Let's go down to the center of it. There it is. And the work that was done really by the people, my colleagues making this movie, was to study how 2 black holes merge. So they did a general relativistic calculation. This is the result. And they showed how to make 2 black holes merge. And at the moment they merge, you get a tremendous burst of gravitational radiation, which creates ripples in space-time. So this is not water waves. You know, it's not like a wave in a material. It's space itself, which is expanding and contracting. And those, as those pass through us, they're passing through us right now, actually. Lots of gravitational waves, because there are lots of black holes merging out in the universe. And the reason you don't feel it is because the distance that they make you move is something like 10 to the minus 20 of a centimeter. So not very much. You're shaking, but you're not shaking very much. However, we do have experiments that can detect these waves by having a test mass monitored with lasers, have the test mass look at how much it gets shaken. It's a very, very difficult measurement. There's a ground-based gravitational wave detector called LIGO. Is that the one somebody here is working on? You're working on that. Yes, LIGO, which will detect smaller black holes in our galaxy. And there's an experiment called LISA, which has the capability of detecting supermassive black hole mergers. But LISA requires a space facilities in space that we don't yet have. So hopefully that will happen, and we will be able to sit in our comfortably at our desks and watch black holes merge across the universe. I think that would be really cool. Each one of them, the result of a galaxy merger. So it'd be like kind of like a movie, almost a movie of the actual evolution of the universe. So I hope I've given you a quick idea of how the universe came to be. And let me just say for the students, there are many, many ways to look at these processes. And so if any of you are interested in astrophysics, there's more than enough work for everyone to come do this. Although what you're doing is really interesting too, so I don't mean to poach. Okay, thank you.